Welcome to Predictive Analytics by Machine Learning. Chapter 5 Data Transformation. Section 8 Dimensionality Reduction. What if I told you that 90% of your data might be useless? That's right, more features often mean more confusion. In this section, we will explore how to simplify complex data into its most meaningful core without losing predictive power. In the last section, we explored target-based transformations, which help encode categorical variables based on their relationship with the target variable. Now, we are moving to dimensionality reduction, an essential technique for handling high-dimensional datasets efficiently. In this section, we will focus on what is principal component analysis. Why do we need dimensionality reduction? How does PCA help simplify complex datasets? Dimensionality reduction is the process of reducing the number of input variables in a dataset while preserving as much information as possible. Many real-world datasets have dozens or even hundreds of features. Too many features can cause redundancy, noise, and overfitting in machine learning models. By reducing dimensions, we can improve model performance and interpretability. Principal component analysis is one of the most widely used techniques for this purpose. PCA is a technique that transforms a high-dimensional dataset into a lower-dimensional space while retaining the most important patterns in that data. It identifies patterns in data and removes correlated or redundant features. It projects data into a new set of uncorrelated variables called principal components. These components capture the most variance in the dataset. Instead of working with dozens of original features, PCA enables us to represent the data using just a few principal components. We can perform PCA in the following 5 steps. First, standardize the data. Since PCA is influenced by different scales, we first normalize the data so that each feature has a mean of 0 and a standard deviation of 1. Second, compute the covariance matrix. PCA analyzes the relationship between variables by calculating the covariance matrix, which shows how features are correlated. Third, compute eigenvalues and eigenvectors. Eigenvalues indicate the amount of variance captured by each principal component. Eigenvectors determine the direction of the new feature space. Fourth, select the top principal components. We choose the most important components that capture the majority of the variance. For example, instead of keeping 20 variables, we might retain only 3 principal components. Fifth, transform the data. Finally, we project the original dataset onto the new feature space using the selected components. As an example, consider an HR dataset with 5 survey questions measuring employee engagement. If these survey questions are correlated, PCA can reduce them into fewer main components. Using this dataset, let's implement PCA by Python. First, import libraries. As usual, import pandas for handling tabular data, and NumPy for numerical operations. Besides, from sklearn decomposition, import PCA to implement principal component analysis. And from sklearn preprocessing, import standard scalar to standardize the features. Then, create a data frame using dictionary and pandas data frame method. Now, we created this dataset. Let's apply PCA to this dataset. The first step of PCA is standardization. This step is important because PCA is sensitive to feature scales. The first line creates a scalar object using standard scalar without inputting any argument. Then apply fit transform. This function contains two tasks, fit and then transform, that is, learning data and transforming data. Fit learns the mean and the standard deviation from each column. Transform applies the transformation to make each feature have mean equals 0 and a standard deviation equals 1. Then, print the standardized version of the dataset. It is now a NumPy array, not a data frame. Next, apply PCA. The first line sets up PCA to reduce the 5 features down to 2 principal components. We need to determine the number of principal components by setting the argument n components within PCA function. Then apply fit transform to PCA. It does two things. Learns the direction of maximum variance, that is, the principal components. Then it projects the standardized data onto these directions. Next, convert the PCA output from a NumPy array to a data frame for readability. We set the column names PC1 and PC2. They represent the new features capturing the majority of the original variance. By displaying the transformed data, we can see that now we have two principal components that represent data capturing the most variance in the dataset. But how should we interpret these components? How much variance do they capture? Let's interpret PCA results using this code. The function explain variance ratio tells us how much of the original data's variance is captured by each principal component. Let's apply this function to PCA model that have learned the data and transformed the data. It outputs a list containing values of 0.979 and 0.016. It means that the first principal component captures around 97.9% of the variance, and the second principal component captures around 1.6% of the variance. In total, these principal components capture about 99.5% of the variance, suggesting that this dimensionality reduction is a good compression. We should know that while these principal components capture most of the variance in the data, they lose the original meaning of each feature, making the results less interpretable. Now, let's look at when to use principal component analysis in general analytics applications. Here, we outline 4 common situations where PCA is particularly helpful. First is when we have high-dimensional data. For example, a survey with over 50 questions or sensor data with dozens of measurements. In such cases, many variables may overlap or measure similar things. PCA helps simplify the dataset by reducing the number of dimensions. The second is when there are correlated features. A good example would be financial indicators or customer engagement metrics. Often, these variables move together. PCA helps combine these correlated variables into fewer uncorrelated components. Third, PCA helps address model overfitting. When a model has too many input features, it can become overly complex and perform poorly on new data. PCA reduces the feature space while preserving as much variance as possible, improving generalizability. And finally, PCA is useful when there is a need for visualization. Reducing complex data to 2 or 3 principal components enables us to see patterns, clusters, or trends more clearly in visual plots. Let's wrap up. PCA reduces the number of features while preserving variance. It works by finding principal components, which are uncorrelated representations of the original data. Reducing dimensions by PCA improves machine learning efficiency and model accuracy. PCA is useful when our dataset has too many overlapping or redundant variables. However, we should avoid using PCA when our features are highly interpretable, like clear categories or domain-specific labels, because PCA transforms them into less intuitive components. Thank you for watching. If you have any questions, feel free to ask in the comments. Your feedback is always appreciated.